All right, welcome back. This is a new day for me, so I bid you good morning. Um, I am just going to do problem 5 to end off this video. Um, Problem 6 looks relatively easy, and problem 7 is CMOS logic. I doubt in my ability to help very much with that. I agree objectively it's not a very hard topic, but I'm not very good at it, so I think you're better off looking externally for that. But I will end off with this problem 5 because it looks a little intimidating, but upon some looking through it, I think it won't be too bad. So let me read out the problem. In the voltage amplifier below, transistors M1 and M2 are identical and operate in saturation with overdrive voltage V overdrive equal to 1 volt. The DC drain current ID through both transistors is 4 milliamps, and early voltage VA is equal to 100 volts. Small signal voltage source VSig and resistor RSig represent an external circuit connected to the input of the voltage load amplifier. Voltage source VB provides a DC bias voltage. In addition, resistors RL1 and RL2 represent load resistances. The component values are shown in the table. Now, the 4 parts of the question are: draw the small signal equivalent circuit of the amplifier, be sure to include the output resistance of each transistor and calculate its value. Part B is calculate the input resistance of the amplifier Rin. And the next one is calculate the small signal voltage gain VO1 over Vsig. And part D is calculate the small signal voltage gain VO2 over Vsig. Now, before I let you go, I would like to draw your attention to the fact that the amplifier, so current comes in here, I guess the voltage comes in here. It changes the voltage at these two terminals, which in turn provides an AC voltage to the loads. I would like to make the argument that this point here doesn't matter. Of course, the voltage there matters for the amplifier, but the voltage here will not affect the amount of current going through this transistor. We've already given that is 4 milliamperes. And this whole part at the bottom doesn't change. It's just DC. So I believe that you can really just disregard the bottom half of the circuit. Okay. Beyond that, I will give you a few seconds. Please pause the video. Try to work through the problem on your own, in whatever that means for you. And I'll be back in a minute. Okay, I don't want to leave you stranded forever, but I do hope you pause the video to give this problem a shot. Now, I will begin with part A. Draw the small signal equivalent circuit of the amplifier. Be sure to include the output resistance of each transistor and calculate its value. Aha. I see. Okay. No problem. Draw the small signal equivalent circuit of the amplifier. So what do we have? We have a voltage source at the top, but in the small signal that will just become grounded. We have a resistor. We have a branch over here which has a capacitor, but the In AC, we just figure the capacitor looks like a short circuit. We have a resistor over here, and this goes to ground. We also have a dependent current source. And then in parallel to this, we have a early resistor. And these go to some negative voltage. However, I would make the argument that since whatever voltage here we have doesn't change the amount of current going through this transistor, I'm just going to leave this as an open circuit. It looks like a resistor with infinite resistance, basically. And then on the side here we have the output 2, which looks like that at AC. Okay, this is R naught. This is GMVGS. And then we have our gate circuit, which looks like this. Just copying down from the question. This is V sig. This is R sig. And this is RG1. Okay. And down here is M2. Now, the output resistance of this transistor right. So, I believe the output resistance of the transistor is, we find that by raising the voltage of the drain a little bit, and then seeing how much more current we get going to the source. So, in that case, I would make the argument that the current through the dependent current source doesn't change, because it's not dependent on this voltage at all. It's only dependent upon this gate voltage here. We'll just call that VG, and this voltage here, which is VS, not upon VD. However, you would still get current going through R0, as well as RL2. So these two resistors act like they are in series. So your output resistance of this transistor is equal to R0 plus RL2, since they are in series. And then for transistor 2, we said that if you change the voltage here, you're not going to affect the amount of current going through. Oh, you would. You would. You totally would. Oh, no. I forgot about the early voltage. Okay. So, as you raise the drain current of M2, you do get more current flowing through here, because basically this has the same configuration. You would get some current traveling through R0. So, I guess I'm going to throw that in. So we have another dependent current source. However, I'm going to say this has 0 amperes because all of the current the AC voltage change here doesn't affect the gate voltage. So it's basically there is a GM here, right? We can say that this is GM VGS, but VGS is unchanging in AC, so it's just GM times 0. But in parallel, we do have R naught. And so you would get some current traveling through the bottom half here. And that would go to ground. It would go to negative VSS, but that's a DC voltage, and for small signals we turn off all DC voltages. Now, we can call this VO1 and RL1 and RL2 and VO2. Okay. So that does change my argument for the output resistance of the first transistor, I would argue. Because if you raise the drain voltage here, you would get current through R0, yes. But after it's done, it could go either through RL2 or through R0. So I'm going to say it's the output resistance R0 plus RL2 in parallel with R0. A second R0 at the bottom. And then R2 is just equal to, so if you raise the voltage here, oh, fascinating. This is quite the problem. All right. So there is R0 for sure. And then in series with RL2 and a second R0. However, that entire possibility is in parallel with RL1 and RD. So the output resistance is that in parallel with RL1, in parallel with RD. And we can figure out what that is later. And then RO2 is R0 in parallel with RL2 in parallel with, so any current going upwards here has to go through R0, but then can go through either RD and RL1. So it's in parallel with R0 plus RL1 in parallel with RD. Okay, those are your two output resistances. And then we need to calculate the value. So I'm going to save this paper. Do I have a second one? No, I don't. I will save that paper because it has the small signal circuit on it. However, I will continue to solve R01 and R02 on a separate piece of paper. So I'm going to bring this away for now. Bring a new paper in, and we're going to say R01 is equal to R0 plus RL2 in parallel with R0, all in parallel with RL1, all in parallel with RD. Now, we have three of those values, but in order to solve this, we're going to need to know the value of R0. And you can see that it's the same equation on this page. In order to find out R naught, we need to use the early voltage. So to draw a quick graph here, what this looks like is we have a certain amount of current flowing through this region as we increase the drain voltage above the source voltage. So originally it looks like that, then it tapers off, it's a parabolic curve. But then after that, once it hits saturation, then it's a linear region. And the slope of this linear region is lambda, which is equal to R naught to the power of negative 1. Or just 1 over R naught. And if you wanted the value of the slope, what you could do, right. So we know that the equation for ID is given as 1/2 Kn, and this is in the saturation region, VOV squared, multiplied by 1 plus lambda VDS. So we would be outside the saturation when VDS is equal to 0. However, we know that the value of ID, hypothetically, at this point, along this line, would be just 1/2 Kn VOV squared, because this term would go to 0, so you'd be left with 1 here. So the height here is equal to ID through the current source only. Then, this voltage here is VA. And that depends only on the make of the transistor. So, if you wanted the slope of this line, what you could do is you could say just rise over run. It's ID over VA. So, and that's equal to lambda. That's equal to your slope. If you wanted your output resistance, therefore, you could say it's equal to VA over ID. Yes, that is one of your more challenging equations. I would recommend memorizing all of this for the final. You never know if we're going to see an early voltage question. But if you have any questions conceptually, please reach out to me. Okay. With that said, let me continue with that. So this is our value of R naught then. And then ID in this case is so we'll say this is ID total, right? And then ID here is only the current going through the dependent current source, right? So this current is equal to 1/2 Kn VOV squared, and then this current is 1/2 Kn VOV squared times lambda Vs. So we could say that 1/2 Kn VOV squared divided by VA is 100 volts, and that's equal to lambda. And then R naught is equal to 100 volts over 1 over 2, and then Kn is Are we not given Kn? We're not given Kn. No. They want to make us solve for it. Okay. So, a tiny quick hiatus. You can see how we need R0 to get the output resistance. But in order to get R0, we need Kn. So, we're going to take a bit of a detour. And then the overdrive voltage, we can use the DC overdrive voltage for that. And that's equal to 1 volt. So 1 volt squared. To find Kn, and I'll get another piece of paper for this. To find Kn, what we should do is we would say that ID total through the transistor is equal to 1/2 Kn VOV squared times 1 plus lambda ID. Now we don't have lambda, but we have an equation for lambda that involves Kn, and that is given here. So I'm going to plug that in. ID is equal to 1/2 Kn VOV squared times 1 plus 1/2 Kn wait, this is VDS, sorry. I'm wondering why I was getting that twice. VOV squared over, I can hear somebody in the background right now saying, you told us to memorize that equation, but you yourself don't know it. Yeah, you make a good point. VDS. Okay. The drain current ID through both transistors is 4 milliamps. So I would say that 4 milliamps is equal to this total current here. And then that's 1/2 Kn VOV squared plus 1/2 Kn VOV squared over 100 volts times VDS. Okay. Did I do that right? Yep. Okay. 4 milliamps equals 1/2 Kn, and this overdrive voltage is 1 volt squared plus 1/2 Kn 1 volt squared again divided by 100 volts times VDS. VDS is going to be equal to VDD. Wow. VDD minus IDRD. And then there's also current going down here. Yeah, no, but you can get the drain voltage. Hmm. Mm-hmm. All right. This is a tricky problem. Okay. To solve for VDS, I'm going to move down here. VDS is equal to VDD minus IDRD. And then that's VD, but we also need VS. So we're going to say that's minus VS. And VS is equal to the voltage at the drain of this transistor. And that value um, hmm. VS VDS equals VDD minus IDRD minus, so basically VS is equal to negative VSS plus whatever voltage the current gains as it, whatever voltage the current loses as it goes from VS to negative VSS. And that is equal to 1/2 Kn VOV squared times 1 plus lambda VDS. Yes, of the second transistor this time. So we have VS is equal to negative VSS plus 1/2 Kn VOV squared times 1 plus lambda V, basically from S to negative SS. Then, to solve for lambda, we're going to plug in the same thing that we had before. So Vs is equal to negative VSS plus 1/2 Kn VOV squared, 1 plus, and then lambda is 1/2 Kn VOV squared over 100 volts. Vs to negative SS is Vs minus or plus VSS. Okay. Now we have 3 equations here. What do we not know? We don't know Kn. We don't know ID. Okay, okay, okay. I think we might still have four unknowns, right? Because, wait a minute. So VS we don't know. ID we don't know. And KN we don't know. So we only have three unknowns. We have three equations and we have three unknowns. So realistically, this is solvable. Practically, a little bit of a monster, but um, I think I think this is where Peter Levine came in. KNVOV squared plus 1/2 KNVOV squared over 100 volts times VS plus 1/2 KNVOV squared over 100 volts VSS. Now we can probably isolate for VDS only occurs once here. So we could use this equation. Did I say we don't know ID? We do know ID. What don't we know? We don't know KN. We don't know VS. Oh, wow. I guess we only have two equations, two unknowns. This shouldn't be as bad. This shouldn't be that bad. So we're gonna plug in we might as well plug in 4 milliamps there. And then in this equation, we only have one term of VS. So we could isolate for VS and then plug that in here and find KN. That sounds like the plan. Okay, so if we were to bring this down, we would get 4 milliamps minus 1/2 KN, I guess 1 volt squared, so that's easy, plus 1/2 KN, no, 1/4 because it's squared, 1/4 KN squared over 100 volts times VDD, which is 5 volts, and that should be subtracted. Plus, in this case, because that was minus, 4 milliamps times RD, which is 20 kilo ohms, and then this becomes 1/4 KN squared over 100 volts and that's all equal to negative 1/4 Kn squared over 100 volts times Vs. And so now we have an expression for Vs in terms of only Kn, and we can put that back into there, and you should get a quadratic. Milliamps minus 1/2 Kn minus 1/4 Kn squared over 100 volts times 5 volts plus 4 milliamperes times 20 kilo ohms 1/4 Kn squared over 100 volts equals negative 1/4 Kn squared over 100 volts times Vs. Then, dividing this by negative 1/4 Kn squared over 100 volts, you get negative 4 milliamperes times 100 volts over 1/4 Kn squared minus 1/2 100 volts. I guess this becomes a plus, a double negative, over 1/4, and then Kn over Kn squared is 1 over Kn. Leave that there. Minus, and then these terms would cancel, so you would get a plus 5 volts, plus, and again these terms would cancel, and you would get, I guess this becomes minus then. Minus? Minus 4 milliamperes times 20 kilo ohms equals Vs. And then, when you plug that into this equation, what you get is this whole thing is equal to negative VSS plus 1/2 Kn VOV squared plus 1/2 Kn VOV squared. We have VOV. 100 volts times, oh no. Plug this back into that. Okay, I'll leave it as Vs for now. Plus, so VOV is just 1. I'm just gonna 1/2 Kn times 1 squared over 100 volts times VSS. Now, to solve this, I would want to move Vs to the other side. So what I'm going to get is negative 1600 milliampere volts over Kn squared plus 12.5 volts over Kn. My units got lost somewhere along the line. Yeah, I'm just going to convert this to 1.6, and then, no, my units should be milliamperes, because Kn is milliamperes. I guess Kn could be amperes. Kn could be amperes. This is 1.6 ampere volts, so I'm just going to leave it as 1.6. The volts goes plus 5 minus AT. Wait, where did my plus 5 come from? That was supposed to be multiplied by 5. Oh, that isn't there. This is up there. No. Oh, I get it, because it's simplified. Okay. Plus 5 minus 80, and that would be in volts, that's good, equals Vs. And then we substituted for Vs. But then I'm also going to move this to the other side. So we get that Vs. So this is all Vs. And then it's 1 minus 1/2 Kn, so 1/4 Kn squared over 100 volts is equal to negative VSS plus 1/2 Kn plus 1/4 Kn squared over, nope, because that term we moved. So 1/4 Kn squared over 100 times VSS. And then we solve for Kn. Multiplying this out, you can get negative 1.6 over Kn squared plus 12.5 over Kn, and Kn is milliamperes per square volt, minus 75 plus 1.6 times 1 over 4 over 100 plus, so that would be a minus now, minus 12.5 times 1/4 Kn over 100 plus 75 times 1/4 Kn squared over 100 is equal to, so negative Vs, oh yeah, okay. VSS is equal to negative 5 volts. So that's 5 volts plus 1/2 Kn plus, so this is 5 divided by 400. So that would be 1 over 80. 1 over 80 Kn squared. Okay. I am not sure how useful this information is, because my result is going to be on the order of a 4th order polynomial. I believe what would have happened is he would have said, this is a take-home exam, solve the 4th order polynomial. I don't know if he intended for you to use Wolfram Alpha for it, but I imagine that's probably what happened a lot. So that is how you solve for Kn. I doubt it would be that complicated on the final.